Okay, so in this second part of the session, we will reason a bit more about statistical inference and try to understand it better how it works. Okay, so uh, it is somehow similar to a legal trial. So the defendant is assumed to be innocent until it is proven that is guilty. So our uh, uh, presumption of innocence of the defendant, it is translated into a scientific problem uh, with the null hypothesis. We assume that the null hypothesis is true, that typically it is that there is no difference, but we have seen that there are different kinds. So this is for significance tests, but we have equivalence tests, we have non inferiority test, we have superiority test. So, but our assumption is that the null hypothesis is true. Okay, then a juror bases his decision only on factual evidence presented at the trial and should not consider any other information, for instance, newspaper stories. So we should collect factual evidence. So in a scientific experiment, the factual evidence is the data that we have collected from that experiment, and we should not consider other data collected in other experiments. So we should not take data borrowed from other papers, for instance. And then, based on this evidence, the juror reaches the verdict of guilty when the evidence is inconsistent with the assumption of innocence. So we have so much evidence that against you that we have to reject the assumption of innocence. So it is the same in an hypothesis test. We have collected so much data. This is the end. So we have collected so much data that the mean of the tablets is different from 250 that I have to reject the null hypothesis that the population mean is 250. And otherwise, if I don't have enough data against you, the juror reaches the verdict of non-guilty. And in a scientific experiment, if my p-value is not low enough, then I have to say that it is not significantly different. But not significantly different doesn't make you equal. So it is the same as in trials. So the fact that I don't declare you guilty doesn't mean that you are innocent. It means that I don't have enough evidence to show that you are guilty, but you may be guilty, but I don't have enough evidence. So it is the same with the null hypothesis in hypothesis testing. And if the juror is not convinced, he can also always say, okay, I'm not sure. So and as a scientist, if you're not sure, if your p-value is not low enough, you can always collect more data. There is a lot of subtleties here, whether to take decisions after looking at the data, all this. But in general, if you're not sure about something, you should collect more data. You should collect more evidence against the null hypothesis. And hypothesis testing and confidence intervals, they are very much related. Actually, they are based on the same theory, and the confidence intervals that we computed for the sample mean. Do you remember in the case of the tablets that we constructed a confidence interval of 95% of probability of containing the true parameter, the true population parameter? Actually, that confidence interval is used to reject the null hypothesis or not. We will see it in a graphical manner now. And actually, let's go for it. So we have observed, this is a different example, it is not on tablets. This is the null hypothesis is that the average temperature, the mean temperature of humans is 37 degrees. So this is our null hypothesis. The alternative is that it is different from 37 degrees. So let's say that we have observed the value that is, let's say, 36.8, and this is our observed sample mean with 12 individuals. Now we construct a confidence interval on this 36.8, and let's say that the confidence interval is like this. And then, because this confidence interval contains the 37 degrees, so it contains the value, the reference value of the null hypothesis, we cannot reject the null hypothesis. Or put differently, if we compute what is the probability of observing this 36.8, if the null hypothesis is true, our p-value would be larger than 0.05. So somehow this limit here is somehow related to this critical value that we had for Z, for the mean, for the p-value that we had in the previous session. And this 36.8 would not be rejected by this critical value. This happens with 12 measurements. If we have 12 people that we have measured their temperature, what happens if instead of 12 I measure 120? We already know from the previous session. So our uncertainty about the mean will be different. So now let's say that the observed temperature, mean temperature, is still the same, but now our uncertainty is much smaller, and then this confidence interval is smaller, and this confidence and these critical values for the null hypothesis will also be smaller. So we would reject the null hypothesis. So what the sample size is doing is enlarging or narrowing these confidence intervals, and calculating confidence intervals for the parameters and for the effect sizes is somehow related to the p-values, and there is a one-to-one relationship between the two. There is a problem that we normally don't think of. That is that the p-value is a much more unstable measure than the confidence interval. And let's say this example. So in this paper here, they were comparing the partial thromboplastin times for patients whose blood clots were dissolved, that is recanalized, and for those whose clots were not dissolved, that they call non-recanalized. And they had observations for recanalized and non-recanalized, and this is the thromboplastin times, whatever that is, and they compared if the mean value of this group is different from the mean value of this group, and you already know more or less how they would do it. It is somehow similar to what we did with the tablets, but now a little bit different because we have two groups and we will estimate the standard deviation from the two groups, not from a preconceived idea, this 1 milligram of deviation that we had before. But okay, the calculation details are different, but the idea is the same. So we will calculate at the end a p-value, and we will take a decision of whether they're different or not. Okay, so we made this experiment only once, so there is no way that we can calculate the distribution for the p-value for the moment. But the p-value is also a random variable. Do you remember that we said, okay, the sample mean is a random variable because if I repeat the experiment with 20 other tablets, I will get similar value, but not exactly the same. So if I repeat this experiment of Miller with different people, probably I will get values similar to these ones, but not exactly the same. And then the p-value in itself is also a random variable. Can I estimate what is the distribution of this random variable? There are statistical tools, in particular this bootstrapping, that would allow you to compute that distribution. Okay, so it turns out that the p-value would go from 0.01 to 0.00. Actually, if instead of the p-value you represent the logarithm of the p-value, or minus the logarithm of the p-value, you see that the p-value goes from 0.0 something to 10 to the minus 7. So there are 6 orders of magnitude here, and so the p-value is terribly unstable. And this is particularly worrying if your p-value is close to the limit. If your p-value is 10 to the minus 14, you don't care if it varies 6 orders of magnitude. It will always be very small. But if it is 0.04, okay, so if it changes so much, it may be that what I'm seeing is just an artifact of bad luck, and then I shouldn't be so sure about rejecting the null hypothesis. And here is an experiment to highlight that idea. So this is simulated data, and hypothesis testing is used everywhere. So this example is coming from psychology, and they are interested in different verbal ability of two groups. So let's say people that read a lot and people that do not read so much, and they want to see if they have different verbal abilities. However, they measure that, and that is a true difference because they are simulating the data. There is a true difference of 10, so the effect size is 10, but the standard deviation of the observations is 20. So we want to detect a change of 10 in a standard deviation of 20. Remind, this is similar to what we were doing before. We were detecting a change of half a milligram when the standard deviation was 1. So it is the same kind of detectability that we want to achieve. Okay, so they simulated data at, I don't know, 10 people in the group of not reading so much, and 10 people in the group of reading quite a lot. And then they computed what is the verbal ability difference between the two. And for the first simulation, they got something like 9. For the second one, they got something like 8. For the third one, they got 8.5. And for some other groups, they got a difference of 20. And if you look at the p-values, you see that you get quite a lot of variability. So they go from 10 to the minus 3 to something that is really close to 1. And there is an actual difference between the two. So depending on what is your sample, you can be very unlucky. And this is an effect of having a small sample size, because if you have a large enough sample size, you would be precise enough to detect differences as small as those. And that is why it is so important to design your sample size based on a power analysis. I want to detect this change, and for detecting this change I need this many samples. And there are two readings or two consequences of this kind of simulations. One is that we see that the confidence intervals, they are much less stable, much less unstable, so they are more stable. So we see that even in the cases where there is no, when we can not reject the null hypothesis, so even this one here, so yeah, it contains, the confidence interval contains 0, so it could be that the null hypothesis is true, but we see that most of the confidence interval is shifted to the right. The same happens here, so it doesn't reach the threshold, but we see that very likely there is a difference, but probably what we have missed is sample size. We are not precise enough, and then, as in the case of the trial, we should collect more data to verify whether this difference truly exists or not. And so better use confidence intervals because they are much more stable than p-values. They don't have a variation of 6 orders of magnitude. And the other consequence is that we should be more strict on the threshold. So because the p-value is so unstable, this threshold of 0.05%, it is quite high. So if you stop your machine, be sure that you should stop it. And if you say that your treatment is effective, really be sure that it is effective. And that is something that you can decide on the design at the time of design. So you design what is the sample size that I need for this confidence level and this statistical power and this difference that I want to detect if it happens. It is not, you're not forcing it to happen, but if it happens, I want to detect it when the level of noise is this one. So designing is really, really important. And also something that we don't think of is normally what happens if we do many tests. And if you think of how many tests you have done along your career, you might be surprised about these results. Okay, so let's say that you're doing some, for instance, drug screening. In drug screening, you test for 1,000 compounds, and in these 1,000 compounds, let's say that the state of nature is that only 10% they have an effect on a given phenotype, for instance. So only 10% of these 1,000, that is 100 compounds, have an effect, while the other 900 they don't have any effect. But you don't know this. This is the state of nature, but you don't know it. That is why you are doing tests with I don't know, animals or cell cultures or whatever. So you are doing your experiments to detect which one of these 1,000 compounds have an effect or not. So you design your experiment to have, for instance, a significance level of 5%, so 5% of false positive rates. The false positive rate is 5%, and you design to have a statistical power of 80%, so a false negative rate of 20%. Okay, so let's look at these 100 compounds that have an effect. Because your statistical power is 80%, so on average, you will recognize that 80 of them they make a difference. So you have correctly identified 80 of the good compounds, and 20 of the good compounds you have missed because you were unlucky with your samples and the p-value was not low enough. And then what about these 900? So these 900s, you have a significance levels of 5%. So that means that 45, that is the 5% of 900, you will have a false positive. So you will think that the compound is really making an effect, but it is not making any effect. So you have 45 false positive, and for the rest, you correctly identified that they don't have any effect. So when you look at your positives, you have these 80 compounds and you have these 45 compounds. So the total of positive tests is 125, of which 45 were incorrectly identified. So that means that the probability of a positive result being an incorrect compound is not 5%, it's much larger, it is 36%. So somehow by making many tests, this is called a problem of type 1 error inflation. So you have many more false positives than you expected by this 5% threshold. So 5% threshold, you would think, okay, only 5% of my cases I will have a problem, but it is not true. You have a much larger amount of problems because you are doing many tests. People working with many tests at the same time, so drug screening or gene expression or these kind of things, proteomics, these kind of things, they are aware of this problem, and then instead of the 5% threshold, they use something different that is called the false discovery rate. Or they somehow protect themselves using this Bonferroni correction that probably you have heard, that is simply lowering the alpha. So if I'm going to do 1,000 tests, I use an alpha that is 5% divided by 1,000. Okay, so do you remember our table where we had what is the state of nature. So the null hypothesis is true, the null hypothesis is false, and what do we decide? We decide to reject the null hypothesis, or we decide not to reject the null hypothesis. And we will call all these cells A, B, C, D. And here I have put the numbers for the example of the drug screening. And here what we have, for instance, is that the alpha, that is the significance level, the alpha is reasoning around this row. So in this row, the null hypothesis is true, and then this 5% is A, that is the probability of rejecting the null hypothesis, divided by the total number of cases in which the null hypothesis is true, that is 900. So significance at this threshold of 5% is if H null is true, so the null hypothesis is true, what is the probability of incorrectly rejecting it? This is alpha. Or put it differently, of all the experiments you could run in which the null hypothesis is true, what is the fraction in which you will reach the conclusion that the results are statistically significant? Okay, what about the power? The power is doing the same analysis, but for the second row. So what is the fraction of tests in which you reject the null hypothesis when the null hypothesis is false? So the treatment or the compound is making a difference, and how many of them I really recognize? I recognize C divided by C plus D. And this is the statistical power, 1 minus beta. Beta is the probability of false negative. So this is a false negative. So the null hypothesis is false, but I don't reject it. So that is a false negative, and that happens 20% of the times. Okay, so the statistical power is what is the probability that if H the null hypothesis is false, what is the probability of correctly rejecting it? That is the statistical power. So the false, the significance level and the statistical power reason by rows. The false discovery rate reasons by columns, and we will not get into these details just to not make it too long, but it is a reasoning by columns. Okay, now all this hypothesis testing, it reminds me of the following problem. So there are 3 variables that are involved, that are the sample size, the effect size, and the population variance. And let's say that you are looking for a tool that is in your basement, and you send your child into the basement to find that tool, and then he comes back and says it isn't there. So what do you conclude? Is the tool there? That is the null hypothesis, or it is not? That is the alternative. So your conclusion on whether you decide the tool is there or it is not depends on how long has the kid been looking for. So if that is the sample size, so if he comes back after 20 seconds, probably he hasn't looked enough. And if he comes back after 2 hours, he has looked a lot. So that is the sample size. So how long or how much you look for the effect that you are looking for. The other one is the effect size, how large the tool is. So if you have to find a snow shovel, it is much easier to find the shovel than a small screwdriver to fix glasses. So if the tool is too small, that is the sensitivity, that is the effect size. If you have to look for a very small effect size, it is much more difficult to find it than if it is a very large effect size. And the other ingredient of the problem is how messy the basement is. So that is the population variance. So if the basement is very well organized, then it will be very easy to find your tools. But if the basement is very unorganized, then it is much more difficult to find your tools. That is the population variance. If your observations have very little variance, then it will be very easy to find this effect size. If your population, if your observations are very variable, then it is much more difficult to detect this effect size. What about not significant results? I have mentioned a few times that we can never accept the null hypothesis. Here is an example. So let's say that Michael Jordan and I went the other day to shot some baskets, and then we shot 7 free throws, and he scores 7 out of 7, so he scored them all, and I hit 3 and missed 4. Okay, so as I'm a statistician, I calculated the p-value, and now the test is different, but it doesn't matter. At the end, it gives you a p-value, and the p-value is 0.07. So if we are not statistically significantly different, so does it mean that we are equal? Probably not. Probably it is the same problem as how long have you looking for your tool in your basement. So with just 7 throws, we don't have enough evidence to say that Michael Jordan and I are different. So failing to reject that we are equal doesn't make us equal. So the null hypothesis is that we are equal. The alternative is that we are different. You fail to reject the null hypothesis. That doesn't make me automatically equal to Michael Jordan. It is the same as in the trials. So you fail to reject the innocence of the defendant. That doesn't make him innocent. It makes him that you don't have enough evidence to show that he's guilty. So a high p-value doesn't make the null hypothesis true. It may be that the experiment was not large enough, your sample size was not large enough, your confidence intervals are relatively wide, and you are not able to reject the null hypothesis. And there is a lot of criticism about null hypothesis and rejection. That is, okay, so there are a few criticisms that we have already addressed. Some of them are related to the p-value is very unstable, so we should use lower thresholds to reject our null hypothesis. And also another objection on all these things of hypothesis testing is that it is very difficult to understand. All this reasoning by rows, different reasoning by columns, it is somehow very fuzzy, and we normally forget about them and don't understand what we are doing. But this is solved by training. And the other objection is on the p-value itself. What are we calculating? So the p-value is the probability of observing the data given the null hypothesis somehow, or related to this, or observing a statistic that is at least as extreme as this one when the null hypothesis is true. But at the end, it is related to probability of observing this data given the null hypothesis. So it goes like this, the reasoning goes like this. So if the null hypothesis is true, then this result would probably not occur because the p-value is very small. So this result has occurred. We have observed it. So then the null hypothesis is probably not true. This has been the reasoning we have been doing. Okay, but this kind of reasoning that in statistics we are somehow it is very abstract and we don't think so well in these terms. But the reasoning line is exactly identical to this one. So if a person is an American, so if the null hypothesis is true, then he's probably not a member of Congress. So there are very few Americans that are members of the Congress of America, of the US. And okay, so this person is a member of Congress. I have observed this result. I have it. So this person is a member of Congress. Then this person is probably not an American. It is the same kind of reasoning that we are doing with the null hypothesis. So the reasoning seems to be very somehow very fuzzy and funny when you put it into Americans and members of Congress. So what you want is the probability that the null hypothesis is true given the data, not the probability of the data given the null hypothesis. But for calculating this one that you want to compute, what you need to know is the probability of the null hypothesis. Actually, this is what we have done here. This is the probability of the null hypothesis. We knew that 10% of the compounds were useful. The problem is that in reality you never know this 10%. You don't know what is the probability of the null hypothesis being true. So you never have access to this, and to calculate this thing you need this one, and you may remember from your college days these Bayesian approaches and Bayesian calculations. So these three quantities are related by Bayes' theorem. So to calculate this one you need this one, but you don't have it. So you have to be happy with, or be happy. You have to live with calculating just p-values. But there is a whole trend now into trying to push people to make assumptions about this one, so that they can these assumptions can be validated or not, and can be discussed or not. But then that would give you a more clear picture of what is if you should really reject another hypothesis or not. And okay, so with this we conclude. So hypothesis testing is a way of automating decisions. To calculate the sample size, we need to know how you will analyze your data. And once you know how you will analyze your data, you will have formulas to calculate the sample size. And you need, when designing your experiment, you have to specify how sensitive you want to be. What is the size of the tool that you want to find in your basement? And how organized your basement is. So what is the effect size that you want to detect in which level of noise? And the larger it is the effect size with respect to the noise level, the easier it will be to prove that the null hypothesis is false, and the smaller the sample size. And by following this procedure, you will decide what is the false positive and false negative rates. So if you calculate the sample size, you know what is your false positive and false negative rate. So because you have designed the sample size for those positive and negative rates. And better use confidence intervals when reporting results rather than p-values. We should be more strict on the threshold for the p-value. 5% is too loose, and there is a reproducibility crisis related to the use of this 5%. It is not the only cause. There are many other causes, but yeah, the threshold and replicability of this instability of the p-value is one of them. Is one of the contributors. And be aware of multiple testing. This is the problem that we had with the drug screening, that your family-wise error of false positive error is much larger than you thought for a single test. And there is a more fundamental problem, that is that we would like to compute the probability of the null hypothesis being true given the data, but for that you need to know an a priori probability of the null hypothesis being true, And because you don't know that, you have to live with the p-value. But the p-value is not something that is really written in the stone. And when the p-value is low, immediately all your life is solved, and you have shown that your treatment is effective. And with this we finish. Here you have more information. Here you have a course on basic statistics, and if you go to video 13 and the subsequent videos, it is where I have taken all these slides. This is a course I'm giving in some other context. And here you have a book on statistical design for animal research that we wrote 4 or 5 years ago. And that would be it. So if you have any question, I would be happy to take it.